In the previous chapter, we studied forces that were balanced. So when you summed all the forces up, the sum was always zero. In that case, an object can either be at rest or moving at a constant velocity. But any of the math that we did, the forces would always, when you add them together, equal zero to show that there was no net force. In this chapter, we are going to allow objects to have an unbalanced net force on them. So we will have non-zero solutions for the sum of the force equation. And what happens in that situation is that you get acceleration. So we're studying forces again, but this time they're going to be forces that will cause acceleration. So they call that whole study dynamics. So before we studied forces at equilibrium, or you could, whenever it's not moving, you could call that statics. So we studied statics, and here we're talking about dynamics. So unbalanced forces, the acceleration is a non-zero value. In this very first section, this is a good spot for us to talk about Newton's third law. We could have actually put this in last chapter. It's kind of a topic that you could put in either place. So that was the overall topic, is going to be unbalanced forces, but in this video we're just going to talk about Newton's third law, and then we'll move on to problem solving and dynamics from there. So as a review, for Newton's laws, we've already talked about Newton's first law in the last chapter, but that was the idea of inertia. So an object at rest remains at rest, or in motion remains in motion. So that was one of those deals where if you had a spaceship that was floating along in outer space and it suddenly turned off its engines, it would continue moving at a constant velocity without any change of direction, no change in velocity. It would just keep on keeping on forever if there were no other forces that were going to affect it. That's the idea of inertia, that an object, once it's in motion, is going to stay in motion. You don't see the spaceship floating at a constant velocity idea here on Earth, because let's say you throw a baseball, you're going to have the force of gravity pulling it down to the Earth. So the gravity there is the outside force that is going to change its motion. So an example on Earth where you have an object moving at a constant velocity, but not like the space thing, would be, let's say you're driving in your car at a constant velocity. That would mean that your engine force is balancing the frictional force, that you would keep on moving on at a constant velocity, and that is inertia. In the same way, if you had a rock sitting there, unless something comes along and pushes the rock will keep sitting there. So that's all Newton's first law was. So that should be a review. Newton's second law is really the focus of this chapter, but this video will focus on the third. The second law is that if there's a net force, you're going to accelerate the object in the direction of that force. So the words are actually a description of the equation. So you can say F equals ma, where F is the net force, or the sum of the forces. The note there, force and acceleration are directly proportional to each other. You can see that in the equation. If you double the force, that's going to double the acceleration, and anything you do to the force does the same thing to the acceleration. That is also true for the direction. So if the net force on an object is to the right, then it will accelerate to the right. So whichever direction you have the net force, the acceleration is the same. So that's another effect of that proportionality. So Newton's third law: for every action force, there is an equal in size and opposite in direction reaction force. You've heard this many times, I'm sure, probably just in the words of, for every action there's an equal and opposite reaction. Notice I put in the words force here because that's what we're talking about. Newton's third law is a law that most people can recite, but honestly a lot of people have misconceptions about. So that's what we're going to be talking about here to get a better understanding of Newton's third law. So when we talk about Newton's third law, here's another way that you could restate it. Whenever object A exerts a force on object B, then object B exerts the same force back on object A. So there's a couple keys to Newton's third law. Newton's third law, you're always talking about the force of one object on another. So there's always two objects involved. We talked about a lot last chapter about the forces on a single object, and when we did the math, those forces were always balanced, but when we did the conceptual ones where we just drew the force diagram, you had some that were balanced and some that were unbalanced, but those were just the forces on a single object. If we kind of zoom out and look at a bigger picture where we have two objects instead of one, you're going to see that however hard something is touched, it has to touch you back with the same force. So that's what we're talking about, and that's kind of a strange concept. Here's one way to think about it that I think is kind of handy to think about. It's impossible to touch something without it touching you back. That sounds funny, but you can't touch the table without the table touching you. That's just kind of the way that it works. You know that it's there, you're touching it, it touches you. It's there's an interaction between two objects, and that's what Newton's third law is all about. So important keys, like I said, the law always involves two objects. And this is kind of a funny thing, is that there's no math in Newton's third law. We saw that there is an equation associated with Newton's second law, that was F equals ma. Newton's third law, there's no equation. Kind of like Newton's first law of inertia, there's no equation for that either, so it's just a concept. Now, sometimes in a Newton's third law question, they'll put a number in. They'll say, if a fly hits a windshield with, I'm going to make up a number, it wouldn't be very much force. Let's say 1 Newton of force, which is probably too much. If a fly hits a windshield with 1 Newton of force, how much force does the windshield hit the fly with? See what I'm saying? Fly on windshield, windshield on fly. If there's a number in the question, the answer is always the same as the number given, which often trips up students. So if the fly hits the windshield with 1 Newton of force, the windshield will hit the fly with 1 Newton of force. It's the same force either way. So I've got a couple examples for you. You always want to think about Newton's third law in terms of action-reaction. So we'll look at a couple examples and do an action force and a reaction force. And this is kind of funny, but always think about it in terms of kind of a yin-yang kind of a situation where you repeat the question back with different words, and you'll see what I mean by that here in a second. A fish swims through the water. So what's the action force? I'd say the fish is pushing the water, right? So that's our action. So the reaction is going to be the opposite of that. The water pushes back on the fish. That sounds kind of silly, but what that means is that the fish has to have the water there or it wouldn't be able to move. Think about this. If you took that same fish and you put it in outer space, which would end badly for the fish, but if the fish were in outer space and were somehow alive, maybe in a fish-shaped spacesuit, that'd be kind of odd. But if there was nothing to push against, if there was no water, no atmosphere, nothing, and it wiggled its little tail, it wouldn't go anywhere. So that's what Newton's third law is, the action-reaction type of a situation. Here's another example, and this one I do hear about occasionally, not so much in our school, but I've heard the situation many times when some teenager gets mad and they punch something. So in this case, I said, angry teenager punches locker. I had a student one time come to class with a broken hand, not at the school, and that's what he told me he did. He said, yeah, I got really angry, so I punched the locker. Here's the funny thing. So your action force is the fist on the locker. So the reaction force would be, well, the locker on the fist. But here's the problem, is the fist on the locker, your fist is going to hurt. The locker doesn't care. So the locker experiences the same force that your fist does, so however hard you punch the locker, the locker punches you back with the exact same force. That is Newton's third law. So, you know, don't be punching things because you only hurt yourself. It's the moral of that story. Here's a long-range one that's kind of interesting. So the Earth exerts a gravitational pull on the Moon. Remember, we've only talked about one long-range force so far, and that's gravity. So gravity doesn't have to touch something to be able to exert a force on it. All the other forces we've talked about so far are touching forces. So here, the Earth pulls the Moon. So that's our action force. The reaction force is the opposite. The Moon pulls the Earth. That sounds funny. Is it true? Yeah, actually it is true. Let's see, I think I had... Yeah, let me skip back. So here's another thing to think about. Let's say that you are at a party and you have a balloon. This is a fun birthday party or something. You hit the balloon. Have you ever hurt your hand hitting a balloon? No. What if you hit the balloon really, really, really hard? Does it hurt your hand? No. And the reason for that is as your hand can try to hit the balloon as hard as possible, as hard as you are strong, but the balloon cannot exert very much force back. It's not very strong. So you can hit it, you know, with as much speed or whatever as you want, but you can actually only exert as much force on it as it can exert backwards. Now, you know, again, relating that to, say, punching a locker or punching a wall or something like that, you see the difference between how you feel, as you know, the effort that you put into that punch versus with the type of material that we're talking about. So that the reason for that, why some things would hurt and some things don't, is Newton's third law, their ability to punch back. So that's pretty much all Newton's third law is, and we'll practice those and talk more about it, but that's a nice little intro for it. So that's the end of this one.